welcome to the one and only EIP dedicated series Peep and Eve, where we discuss an Ethereum improvement proposal, understand its importance, and talk about how it is going to make Ethereum even better. I'm your host Pooja Ranjan, and we are joined by William Schaub, Alita Moore from Ethereum Cat Herders, Ratan Rai from Consensus, and our hard fork coordinator James. In 2021, most of the people in crypto space seems to be going bullish on the price. So we thought of going bullish on the upcoming proposals. Today, instead of one, we are going to learn about two proposals. EIP-3102 binary trie structure and EIP-2584 trie format transition with overlay trees. And our guest is Guillaume B. Both EIPs are standard track core proposals and are in draft status. How close these proposals are and how they are going to help Ethereum chain, let's hear out from the author itself. So without further ado, let's welcome Guillaume. Please let our audiences know a little bit about yourself and then we'll dive into the proposal.
Yeah, sure. Thanks for having me. So my name is indeed Guillaume. I have been with the Ethereum Foundation working on the Go Ethereum client. And more recently, I've been focusing especially on the state, which is growing. Yeah, so there's a lot of efforts happening in the guest team right now, trying to, and actually in the whole community, I should say, trying to do something about the state, the size of the state, and at least make it more usable. So this is what those two EIPs are supposed to address. And yeah, so I'm going to present two EIPs. I mean, mostly one. The other one is a bit more a back burner for reasons that will appear evident, well, hopefully. And so the first one is about switching from Hexary trie to a binary trie. Actually, both of them are, but this one defines the structure of the binary trie. So just for those, for whoever might watch this video later and doesn't know what the Hexary tree is, it's basically a tree in which each level has 16 children. So that means that each node has 15 siblings. So the advantage of this approach, and which is why it was picked up at the beginning, is that it's more shallow. If you compare it, for example, to the binary tries, which are much deeper, and unfortunately, you can't even see the bottom of the picture. That's the data. That's a tree that represents exactly the same thing as the previous one. But you can see that the binary tries or trees have only one sibling. Which is a property that is really interesting if you're moving into what's called the light client. So you only receive a little bit of the state and the proof that this corresponds to the root. So to get the proof, you need to provide all the siblings at every level. And if you have a tree that is wider, you will have 15 siblings at each level, whereas one sibling at each level, in the case of a binary tree, is actually saving space. It's saving four times, roughly between 3 and 4 times the space, at least theoretically. So that's the role of this EIP to propose what will be the structure. How do you organize the whole tree to keep all the benefits and to reap the benefits of the binary trees to build more efficient proofs. So the key points of this EIP, well, obviously it's about using binary trees. It's about changing the hashing algorithm from Ketchak 256 to Blake 2. It's about getting rid of RLP, which was something everybody, by popular demand, we got rid of RLP, and there are two more things. Like we put the key at the leaf level, but I will explain that a bit more in details at the end of the presentation. So yeah, the binary tree. Sorry. Like I said, smaller proofs. It's also the structure of choice for ETH2. So whatever brings ETH1 closer to ETH2 is always nice to have. There's a lot of simplifications that I will show can rolled in thanks to that structure. And as I was saying, there's a lot of like the depth of the binary tree is much bigger than the depth of a Hexary tree. But actually, there's a lot of optimizations that after using the Hexary tree for 5 years now, we realized that a lot of the reasons why Hexary trees got picked up in the first place over binary trees, a lot of those nice to have or those nice properties can actually be optimized in binary trees to provide the same amount of benefits. And the problem of binary trees is okay. Actually, let me skip over that. I will get back to this in a few minutes. So, like I said, one of the most awaited request or feature of this proposal is to get rid of RLP. So RLP is the encoding method of for many things in Ethereum, but including the nodes in the database. So we just get rid of it. And the reason for that, the reason why it was chosen in the first place is because if you have 16 siblings and let's say most of them are empty, if you take a fixed structure with 16 entries or 17 if you have a value, you find yourself having a lot of space taken, and most of which is empty U256, like 32 bytes, sequences of 32 bytes. And as a result, there's a bit of compression. So RLP was actually used in this case for compressing nodes. But in the case of binaries, when you only have binary trees, when you only have two nodes, two children, you don't really need this compression because each branch in the tree will always and systematically have two children. So the compression really does not exist. So the proposed structure is just a pair of two 32-byte integers or U256. And depending on the type of node, those two values contain something else. And this fixed structure is also nice because it's got some, apparently it's easier to build, to make ZK like zero knowledge constructions out of this. So this is also something that was requested. So in the case of a branch in a tree, well, it's simple. The first word is the hash of the left child, and the second word is the hash of the right child. If it's a leaf, we put the key. So this is something I already hinted at, and I will detail later. But the first value is the key, and the second value is the value of stored at the leaf. And then we have extension nodes, which in practice are merged with their child node, and you just store the length of the prefix and the hash of the child. I was also talking about Blake 2. So why did we pick Blake 2? We made some measurements. So you have four plots with different tree sizes, and every time you can see that the use of Blake 2 as a hashing algorithm is actually 4 times faster. I mean, roughly 4 times faster as the Ketchak one, which is nice because it compensates exactly the length of a path from the root to a leaf. So that's something nice. And the reason why you have something so small on the left side and something so high on the right side is because one method was using extension nodes and the other one was not. So there's been a big debate, but I'm not going to delve into this for the presentation. Right, so I was talking about merging the account and the storage trees. So in Ethereum, you have a lot of trees that are more or less independent. I'm actually not sure why they were separated initially, but it makes sense to merge them simply because if in order to access slot storage, the slot of an account, you prefix it with the address or the hash of the address of that account. So if it's all stored in a subtree, when you store everything in a database, everything is contiguous. So you can like load the account and part of its storage directly from disk in one go. You don't have to do a lot of DB searches in the DB, so it's a bit faster. It reduces I/O, and I/O is the killer when it comes to performance. And also there's another EIP, I forgot to check the number, it's 29 something. It's about code Merkleization. So one of the ideas is, instead of passing all the code to a live client, you only pass the bits that are really needed for the execution. And this is another tree, so it starts looking like you have too many independent trees, so might as well gather, bring them all under one tree. Right, so this picture is a bit cut off. Let me see. I don't know if you can see. Yeah, it looks like you can see properly now. So the question is, how do you access all those info? Because, like I said, there's a very fixed structure of two 32-byte integers. And the problem with this is that you can no longer have values inside the inner node of a tree. So what we propose is to actually put all those values in separate locations, in separate leaves. So the balance, the nonce, the code, and the root of the storage tree for an account are all accessed at different addresses. And those addresses are all related in a way. You just pick the last 2 bits of the hash of the account's address. The hash was already used in Hexary trees, is to keep the tree balanced, to make sure that no attacker will be able to write a lot of create a lot of accounts, or a lot of store a lot of data in one location of the tree, to make it very unbalanced and therefore hard to access. So we save this hashing part for that specific property, but we keep we clear the last 2 bits of this first 32 byte address to select as some kind of selector to get the item in an account. So the balance is 0, the nonce is 1, and well, the code right now is a big blob of data, but if the code Merkleization happens, it will end up being the root of the tree whose leaves are representing the code. And when it comes to the storage tree, instead of having 32 bytes addresses, you have 64 bytes addresses, so 512 bits. And you also do the hashing, because you have this two-level hashing, which was already present in the Hexary tree, and is necessary for keeping the tree balanced. And the last, no, actually, is it the last? Yes, the last optimization, or the last point I wanted to talk about for this EIP is why did we decide to put the key at the leaf level? And it's simply because, well, the key is already, when you search inside the tree, you already have the key handy. And doing all this, putting it like in the Hexary tree. So in the Hexary tree, you have chunks of keys all over the internal node. So the key is split, and it's actually split into nibbles, so four bits, packs of 4 bits. And you find yourself having to shuffle data around, like because if it's on an uneven nibble, you have to shift everything by 4 bits. So there's a lot of data manipulations, which also end up being very complex, error prone, consuming, and we didn't want to time consuming, and we didn't want to go into this trouble again with bits, because now instead of having 1 in 2 chances of having to shuffle the data, you find yourself having a 1 in 8 chances of having to shuffle the data. Lots of complexity. There's a whole article I wrote about this. So yeah, we didn't want to go into this. And like I said before, I was talking about the flat database, or at least I was hinting at the flat database. So instead of storing everything in the tree, what we want to do is just do it like TurboGeth is doing it, which is just have a linear storage of key and values. So because, since the key is right next to the value, might as well put it in the tree representation. So what we found, at least what Alexei from TurboGuess found, is that yeah, getting the data from the disk was actually the performance killer. Rebuilding the trie, recalculating the root was faster. So this new EIP assumes this approach. And I just wanted to explain or to pinpoint one specific detail. So we're not putting because we're not doing bit shuffling. Instead, we're doing the length of the prefix. But what we're doing is not to put the length of the prefix at the node level, but the length of the prefix from the root to the subtree. And I have this illustration that I'm going to walk you through. I don't know if you can see my mouse pointer.
Yeah, we can.
Okay. Thanks. So the first model where you have just the length of the prefix at the node level. So suppose you have a tree with only a key of eight bits. You have a first fork, so you choose the right one, so that's 1 bit, right or left. Then you have a prefix of 4 bits, so that's what's stored here. And then you have another fork in another branch, so it's either it's 1 bit for either right or left. And then to complete the full byte, the full 8 bits, you need to have 2 bits here. And if you delete the red square, what happens is that you need to recalculate this node, because the extension moves, like the prefix moves, changes from 4 bits and 2 bits to 4 bits plus this bit plus those 2 bits, so that's 7. So you need to actually update the sibling node. And that's not great. Well, first, because there's a lot of I/O associated to this, and second, because in proofs it creates a lot of very tricky problems. So what we do instead is to provide 5. So that's 1 bit plus the 4 bits that were here. It's 5, and then you have another bit plus the other 2 that were here. So you reach 8. And if you delete this node, well, you had 8 here, and you still have 8 here. So you really don't need to change that node. So that was an optimization I wanted to make clear, because I really think it's a nice one. Right. So that was it for the structure of the binary tree. And now I just want to quickly go over 2584, which just describes the method for converting from a hexary to a binary tree. So this is actually the one that started everything. And while I was working on this one, I realized there was some lack of clarification as to the structure of the binary tree. So this is why I created 3102. And this one is a bit, as a result, is a bit on the back burner, because the previous one is asking a lot of questions, needs to have a lot of things clarified, and is very complex. So yeah, I'm just going to explain how it works, but at the same time, it's a bit on the back burner. So the idea, which is actually taken, I don't know if people have been using or have been looking at the way Docker works, for example. It's layers. So you have read-only layers, and you have the top layer, right? So it's the way file systems work in Docker. You have layers representing files, several layers, and the file system at the top is writable. So if you write to the file system, it will end up in the overlay layer, the layer at the top. So we do the same thing. We have the hexary tree, and we have the binary tree. And there's something I should have explained. Sorry about that. The problem: why don't we just convert everything in one go and be done with it? It's because doing the conversion on my benchmarks takes roughly a day to convert from hexary to binary. So this is based on Geth, which is a very like the way we built it in Geth really wasn't meant to do this kind of approach. So this is why it's extremely slow. But because this is the current reality, you have the problem that as you start covering all the keys and building the new tree, someone like blocks still need to execute, and because they still need to execute, they might update values in a part that has already been converted. And there's a bit of a locking issue. It's not really nice. And as soon as you get locking, consensus issues are not far. So we wanted to avoid that. So
and blocks are 14 seconds. And
yes.
So a day
right.
compared to 14 seconds is a lot.
Exactly. Thank you for pointing that out. Right. So because you can't fit a whole day in 14 seconds, indeed, you need some kind of alternative method. And so the idea is indeed to have all the writes go into a binary tree that is laid over the Hexary tree. So every time you write, it ends up in that tree. Every time you read, it will first search in the binary tree. If it can't find the value, it will search in the Hexary tree. That can be done in parallel, of course, but this is how it proceeds. And there's a consensus change here, which is why this EIP is a bit controversial. You need because you have two trees, you have a base tree and an overlay tree. You need to have two values in the block, two state roots in the block. So yeah, that's a bit of the question, or at least the thing. Sorry, I'm looking for the word. The criticism that has been raised during the review. So like EIP-2, the process has three phases, and the first phase is the one where all the writes end up in the binary overlay, and meanwhile in the background, all the base tree, which is read-only, so no longer changes, is being translated n blocks, so n items per block so they're basically read from the Hexary tree. Like you read n leaves from the Hexary tree, and you insert it into a binary tree that is not really published. Could be added as a header, but doesn't have to be. And in fact, it doesn't have to be n leaves either. It's just that basically n leaves is the minimum number of leaves that need to be translated at every block. And so after a while, when we estimate that clients have had enough time to process everything, so that's basically n times the number of leaves, or n times the number of blocks. When that value gets over the size of the Hexary tree, you switch to phase one. And in that case, you just replace the base tree, the Hexary tree is deleted, and it's replaced by its binary equivalent. And then every block, you have n keys or n values that are moved from the overlay tree, so deleted in the overlay tree and inserted into the base tree. And when you write, you go directly into the base tree. And of course, if you write a value that is already present in the overlay tree, it's deleted from the overlay tree. So and the last
what's the difference between the overlay tree and the base tree in phase one?
In phase one, so what happened is that in phase 0, the overlay tree was the one that was read and write, and the base tree was read only. And that's the other way around in phase one. So the overlay tree is presumably much smaller because it's only maybe a day worth of writes, whereas the base tree is like 5 years worth of writes. And so you just it's basically the same process, but it's the layer that is read only and the layer that is written to are inverted. Yeah, you were very faint, so I don't know if you're still talking.
No, I guess I don't understand why the two phases are necessary. Why phase one isn't directly writing the final binary tree.
Right. So that's because it's for parallelism. Because you don't want, if you do this, if you write both together, you still have the problem that you need to write back. Like if a value gets written into the tree, you need to like the conversion happens and you still have the problem that you might write, like you might have to recalculate things. So it's really just because it's to simplify the merge, basically. It's yeah, so that you can do both in parallel. You don't need to lock. All right, because okay, let me re-explain that in a more in a simpler way. If you want to do them in parallel, they have to be separate. If they are not, if they are written in the same tree, you need to make sure that either, like basically they need to be sequential. Either you do the end translations first, and then you execute the code. So that means more delay for creating the block. And yeah, so it's better for miners, basically.
I see. Okay, so one of the two is in. Okay, I see.
Right. It could be done. Yeah, it's just it's an optimization that maybe has no has no reason to exist. But yes, that's the reason. Yeah, and so phase 2, it's simply yeah, you just drop the extra header because it starts when the overlay tree is empty. So when the overlay tree is empty, you just drop that extra header, and you're done. So the question is it really worth it? So at the time I created this EIP, the answer, in my opinion, was yes, because it took a day to do the conversion time. But since Geth is slowly moving to a flat DB approach, where it just takes roughly an hour to recalculate the root hash in a binary context, it might not be as necessary. I mean, I still think the approach has its merits, but it doesn't need to be enforced in consensus. And that is basically, it's Peter who there was an issue that Peter had with this. And I agree, given the fact that it's just for 1 hour, we can still have like the chain operating. The algorithm itself is correct as far as I can tell, but it doesn't need to be part of the consensus, which means you could do all that merging and like in the background, and then just publish it, like move from Hexary to binary. So I would say I'm less enthusiastic about this EIP at the moment, but the real question, like the real decision, whether it's abandoned or not, will be clear when EIP-3102 is complete. So yeah, that was it. And yeah, that's pretty much all for the presentation. So yeah, if you want to join the discussion, there's this thing. Oh yeah, on Medium, I tend to write some articles about this that try to be a bit more accessible. So there's two of them in the pipe right now. So hopefully they'll come soon. And there's a PR that I wanted to show. So currently the 3102 has been implemented. There's still a huge to-do list, but the basic logic is here. So that's the one if people want to implement their like try it in their own clients. This is the one to look at and to criticize. It's by no means perfect. In fact, it's not even passing lint. But overall, like the general logic is here. And yes, if I wrote an article about explaining in detail why we are dropping RLP. So that could be interesting as well. And with that, oh yes, there was another question that I was supposed to answer. It's when do we move to the next step of the EIP? Well, basically when this PR is done, and we also need other clients to try this EIP and give us feedback, because we don't want to be I mean, I don't want to be making the decisions for every single client out there. So there should be some implementation based feedback, and when we get that, I think we're ready to move to the next stage. And yeah, this time I'm done.
That's awesome. I had some kind of more general questions to help people follow along.
Mm-hmm.
Like where would you say the tree fits in the Ethereum stack of development, and like why would people care about this work happening?
Oh, well, the thing is, it's a bit difficult to answer because there's so many, I would say everywhere, like I'm trying to not answer everywhere, but yeah, if we manage to, one of the biggest, there are two main axes in which like the general public would be interested. First, it's the size of the syncing and the Ethereum mainnet on their disks. Because if we start using the flat database, there's a lot of operations that will, like a lot of download. The sync will basically become easier, and the data requirement will become smaller. And the other thing is, like I said at the beginning, it's everything that is light client related. So if you want to be able to use Ethereum on mobile or in a lighter clients, or you just simply don't want to go through like hosting all of the internet's data, and you're just interested in your own data. So there's a lot of usability tweaks associated to this. So it's very, I agree, it's very, very core, very boring details for most people, but it will have an impact on usability.
So the way that I would normally like consider a binary tree would be like just simply for sorting, right? And just, I guess, to clarify, is the primary point of this binary tree to make finding information like a lot less computationally expensive? Because I remember you mentioning that for TurboGet, the primary performance holdback was the memory access.
The disk access, but yes, that's I mean, trees are an ordered data structure, so yes, it's for searching, it's for searching your data. Does binary trees in general make searching faster? No, they don't. But because of that flat database that we're switching to, it's not going to have an impact. Like basically the switch to the new database model is the one that is going to provide the performance, and therefore the binary tree performance is fairly irrelevant, and therefore we can adopt a simpler structure. So it's basically more of a maintenance code maintenance issue.
Okay, so then just to like kind of clarify, what you're saying is that the binary tree, like its primary purpose is that it's compatible with a significantly more efficient database or state management system for Ethereum?
Not exactly. Like it's really just the choice of the new database format that lets us pick whatever tree format we want, and we're just gonna pick the format that is available in every textbook, that is well understood, that is like there's a million implementation, a very good implementation. So it's just simpler to conceptualize.
Sorry, if I could just jump in. I think the question was why this change to binary trees. Like, what's the primary motivation? I think the primary motivation is witness sizes.
Witness sizes, absolutely.
That it is fewer hashes has to be provided to
right.
prove that something is somewhere in the tree.
Yeah. So sorry, I did not understand the question, but yes, that's that is the main motivation.
Do you mind giving like and anyone else can jump in and interrupt me because I'm kind of just trying to explore for myself. But like, do you mind explaining step by step how like when it would be required for this proof and where how that would happen, if that makes sense?
No, sorry, could you reformulate, please?
Sure. So Donkrad just mentioned that that like the primary motivation is to reduce the amount of like processing requirements to provide a proof that a certain transaction or feature exists within the entire tree, or within the entire Ethereum like history and state. And so my question is like, how does one normally compute that proof, and how does the binary tree like make that different?
Right. So yeah, so if you, for example, if you want to see that node here, to compute that proof, you need to give the hash of all those values here and all those values here, and then the hash of all those values here and all those values here, and then the hash of the root. This is how you compute the proof. So you can see there's a lot of siblings. There's 15 per level. And if you use a binary tree, you have only one sibling per level. So the depth of your tree is 4 times as, the tree is 4 times as deep, but the number of siblings is 2. So you only have, instead of having 15 times 2, you have it must be 8 times 2.
No, not quite. It's
sorry,
less
8
than that,
times,
because you don't need to provide the child that you're proving. You only need to provide the siblings.
Right.
So
But
4.
okay, 4. Yeah. So that's basically the approximation. So it's just 4 times smaller. It's an
you lost me a little bit there. Specifically,
I might be able to try a so in correct me if I'm off on this stuff, guys, but everything that's ever happened in Ethereum, whether it's your account, how much ether you have, how many ERC20s, like where you are, somehow fits in this tree, and each block something happens. Like if I make a transaction, something happens to those trees. Usually there is some access that's having and changing to the storage. But there is, the state of Ethereum is huge. Every block, not everything's always going to be touched. So if you can only pick the parts that are being changed and then have that be part of what's being stored or proved, then you can have a lot smaller thing than trying to save the entire tree the entire time, every time, or share the entire tree every time. So if you're trying to find something in a binary tree and define where it is, it's a lot more compact to be able to do that with the binary than the hexanary, because you don't have to have the 16 steps. Like you just have the 0, 1, 0, 1, 0, 1, you're there, kind of a thing.
that makes sense. So then what you're saying is, like, instead of having to prove the entire every I guess what I'm trying to say, every piece of information on the tree to prove that one occurred, you just have to prove that the single I guess branch of the tree exists, and that's like the major difference.
It's just how much of the tree do you need to be able to get to have to access all the places that you're trying to change. And in a binary tree, that's a lot smaller.
Okay.
Right. I was wondering, maybe Alita's question was more about, like, why does that matter? Why does it matter that the witnesses are small? I'm not sure is that your question, or?
Yeah. Yeah.
Right. And
because,
I mean, the answer for that can be different things. Like, one is, for example, you want to know how much ether do you have in your account, right? And you can just ask a node and they give you an answer and you can trust them. But with this structure, you can actually get something better. You can ask the node, and the node can say, like, well, from the current root hash of Ethereum, I can prove it to you. I can show you that this is correct. This is the witness, and that's becoming smaller. And this matters even more because in the future, we might want to go to a world where every block actually includes complete proofs that the changes that were made to the state were done correctly. And these would become a lot smaller in this structure. And that means you can validate a block without even knowing what this huge, like, many gigabytes of states are. You can just look at this block, a few megabytes, and see, aha, it's corrected. This is the correct Ethereum block.
Thank you very much. That makes sense.
I have one question about the hash function. So it seems a surprising choice to introduce yet another hash function into Ethereum with Blake 2, because we're going to use SHA-256 for ETH2. Like, have you thought about just using SHA-256? That would have been maybe the obvious choice.
That was indeed considered. That is still considered. The reason why I picked Blake 2 is simply because it's much faster. But it's true that yeah, I mean, this is a good argument that it's going to be used for
How much faster is it?
4 times.
Okay, and this is because like many modern CPUs have acceleration for SHA. Did you take that into account? Is that used?
That's true. I used it on a on an older CPU.
You should check that, because modern CPUs often have like instructions that do a large part of a SHA computation, so that really matters.
Okay. That's a good point. And yeah, the reason why I haven't really looked into this because I'm not sure Go is going to optimize for that, but actually it should. Yeah. Okay. Good point. I will have a look. That's a very good point.
Great. So before we can go ahead with the non-technical question part, so I would like to give this opportunity to anyone participating here. Do you have any further question on this? Okay, so moving on to the next section that is related to the EIP processes. The cat headers are also involved in the process improvement of EIPs and network upgrade. So with this series, we are trying to share information about the latest processes that are being followed. And we have recently published a couple of blogs on ECH Medium explaining the EIP standardization process and the network upgrade process. Talking about the statuses for these two EIPs, according to the EIP, it is in draft status. Recently, a status review has been introduced that is in between draft to the last call, right? Mm-hmm. So as per one EIP1, the review is like whenever an EIP author marks an EIP to be ready to be reviewed by peer review, we can move it to that state. Do you think these proposals are in the stage that can be moved into review?
The 2584, I would say no, because it's really dependent on the 3102. 3102, yeah, I mean, I think we're already technically way into review. So yeah, that would make sense.
Great. In that case, like this would be a request that if you get a chance to move it to the review status, that would be really great. In case, like we have experienced that there are proposals which are ready to be moved from one status to another status, but due to other priorities of author, they do not get to move it, create pull request for that. The cat herders have helping out with that changing of the PI status with author's permission. This is just for the information of all other authors out there whose EIPs need status change. If you need help, please reach out to EIP Ethereum cat herders. We just want to make sure that whenever community is reaching to eips.ethereum.org, they should get all the correct information there. So the next question I have is related to a discussion to link. As per the current EIP, both the EIPs points towards ETH research, which is really good place for technical discussion. But because these EIPs are standard track core proposals, we hope to see them in one of the future upgrades, obviously after Berlin, I don't know when, but yes. So this will invite more community participation, consensus, and visibility, like more than the present technical set of people. So we generally recommend to point EIP's discussion to the Fellowship of Ethereum Magicians. What are your thoughts on moving the discussion to link? Maybe not, maybe later when it is ready, or move to other statuses.
Yeah, no, I mean, there's no problem in doing this. Especially getting community feedback is always interesting. I still think ETH research is the place for technical feedback. Although, yeah, Ethereum Magician is not a bad place either. No, okay, I can do that.
Sounds good. Thank you so much. I mean, I really enjoyed this conversation today.
Well, thanks for having me.
Yeah, thank you everyone for adding value-adding questions and comments that I'm sure is going to help other client implementers who could not join us today. So for devs who are working on this binary tree or planning to write a new proposal involving binary tree or EVM, there is another episode we recorded in December with Nick Johnson that would be having some useful information. If you haven't watched it already, you can watch it on Ethereum Cather's YouTube. For community watching to learn proposal, do let us know if your comments, if you have any questions that could not be answered in this episode, you can ask the author directly. His Twitter handle and links for discussion, as well as the presentation that was shared today, would be provided in the description section. So we started this Peep and Eep series late in 2020, and we received pretty good responses from community. For 2021, we have got quite a few interesting proposals lined up. Next week, we will be joined by Alberto Canada to talk about an interesting ERC, that is EIP-3156 flash loans. So stay tuned, keep sharing your love with Ethereum cat herders. If you like this series, do hit like, share button. Do not forget to subscribe to Ethereum Cat Herders YouTube channel. This is all of us signing out.